Good evening, ladies and gentlemen. Good morning. Good afternoon. Today we're going to do this video on Newton's method, also known as finding roots. It's a way we use the derivative to help us solve equations. The assignment is going to be on 3.8, and it'll be numbers 1 through 18 even. So, here are 9 questions you can choose to ignore, or actually do, because actually this is a pretty really neat and quick and easy application of derivatives. Ladies and gentlemen, let's get started on what this means for us. Well, let's look at a graph of this right here, and we have a tangent line. That yellow line is the tangent line, and that tangent is tangent at x sub 1, which is right there. Newton's method is based on the assumption that the tangent line and the graph of f of x cross at approximately the same point. Now, I had alluded to this earlier about how tangent lines and the actual function it's tangent to do cross around the same place on the x-axis. And if you look here, we have a red dot, which is C, and an X, which is labeled right there. It's a little blue dot. These are really close together. And the better approximation we get, of course, the closer is the approximation of the line to the actual function. It seems kind of weird, but this is called linear approximation. And believe it or not, this is used in a lot of different fields, from the medical field to a lot of basic statistics stuff that people use in like crime labs and stuff like that. Because we can't get an actual time of something happening, we can approximate it by looking at a function, especially if what we're looking at has a pattern. And in this case, we have this nice little parabolic pattern, and this tangent line will pretty much be an overestimate, but still be a pretty good estimate. Okay, let's go ahead and look and see what else happens here. So, all right. Now consider the point-slope form of the equation of a tangent line. This is the only way we've been writing equations of lines, and that is y minus y1, or in this case, f of x sub 1, equals the derivative of f of x sub 1, which is basically the slope, times x minus x1. Okay? We'll put this in function notation just to kind of speed up the process on the Newton's method that we're doing. What we're going to do here, ladies and gentlemen, is we're actually going to solve for y. So to solve for y, ladies and gentlemen, what would you do? Not everybody at once. Exactly. We're just going to add f of x sub 1 to both sides. Okay? And so y is going to equal f of x sub 1 plus f prime of x sub 1 times x minus x sub 1. This, ladies and gentlemen, is going to be our linear approximation. It's using the derivative of the function and the tangent line of that function. We're going to let y equal 0. And why are we letting y equal 0? Well, we let y equal 0 because this is the x-intercept of the function. So if we let f of x, let y equal 0, now, ladies and gentlemen, what we're going to do here is we're going to solve for x. Okay? We're going to solve for x now. So to solve for x here, ladies and gentlemen, simply subtract f of x sub 1 from both sides. We're going to divide by the derivative of f of x sub 1. Okay? And last but not least, we're going to add x sub 1 to both sides. When you do this, this results in this equation down here, which is what we'll call Newton's method. It is x equals x sub 1 minus f of x sub 1 divided by f prime of x sub 1. So essentially, an x value times the y value corresponding to that x value divided by the slope at that x value. This, ladies and gentlemen, will help us approximate any value of a function using a straight line. Okay, we'll see some practice in a second. So here is our Newton's method approximation. X sub 1 is the initial guess. Now, when I say initial guess, that's exactly what I'm going to tell you is like, hey, take a really good guess of where you think the line crosses the x-axis. Okay? It should be really close to the 0. However, I'm going to tell you, you can be kind of off sometimes too. And using Newton's method, it will get you closer and closer the more times you use it. We could continue to plug in the result. So once you plug in your guess and get an answer, you can take that answer, plug it back into Newton's method until you're satisfied that you found the root or the solution to the equation. You know, in other words, once you feel like, wow, my guess is really close, and you're within 3 decimal places of the actual answer, you're good. And you'll know this because you'll see that the 3rd decimal place won't change very much. And again, this is all fun, but it's better to see it in an example form. To apply Newton's method, the following must be true. F has to be continuous between A and B. And F has to be differentiable on the same interval, A to B. Now, notice that these 2 criteria are also criteria for the mean value theorem and for the Rolle's theorem. But this 3rd condition I'm going to give you is different. Rolle's theorem says that f of b and f of a have to be equal. Mean value theorem doesn't make any requirement on f of a and f of b. They just have to exist. Newton's method requires that f of a and f of b differ in sign. In other words, whenever you are trying to do this linear approximation on an interval, you actually have to go from a positive to a negative or a negative to positive. And why is that, you might say? Well, earlier in the year we learned about the IVT, or intermediate value theorem. And the intermediate value theorem stated that if you go from a positive value to a negative value on something that is continuous, then you're guaranteed that there will be a 0 somewhere in between. So between a positive and negative, there has to be a 0 if your function is continuous. And that's what Newton's method is trying to find. It's trying to find the zeros. So your endpoints have to differ in sign. One has to be positive, one has to be negative, and not in that order. It could be negative and positive. If the approximations that Newton's method produces approaches a limit, then the sequence that you're using, the sequence of guesses that you're using, is said to converge. And if the limit is c, if it converges to a certain value, then f of c is going to equal 0. And what that's saying is, the more times you use Newton's method, once you get it to a place where the 3rd decimal place doesn't change, what this is telling you is you've actually found the actual root, or a very good approximation that, you know, the human brain can understand as an approximation to an x-intercept. All right. However, there is a little pitfall. If the sequence fails to converge, in other words, let's say you start sticking in these values and you're doing it correctly, and it doesn't converge to a single number, like it goes from 0.5 to 0.6, then it goes to 0.8, 1, 2000. If it fails to converge, then Newton's method fails. There's a couple reasons for this. There might be a horizontal tangent, okay? A horizontal tangent would mean it's parallel to the x-axis, so therefore you won't get a value. Or there might be a vertical tangent, in which case, if you remember from chapter 2, vertical tangents mean that the limit doesn't exist and the derivative doesn't exist. Okay, undefined slope. Lastly, Newton's method can be used to approximate points of intersection. So If I want to find where two lines cross, I could just use Newton's method. And to do this, the simple conversion is you take a new function, h of x, which is equal to the two functions subtracted from each other. Saying, well, why are we subtracting those two from each other? Because we want the distance between those two functions to equal what? Well, if you said 0, you're right. So we're still finding zeros, but we're finding zeros of the zero of the difference of two functions, which means how far apart are they? And if we see that two functions are 0 apart, we can approximate that actual root. Okay, we will do some examples like this in class. I have some really good examples to show you, and this method is super easy to use, and there's at least 3 questions on the test. One in the free response and a couple in the actual test, multiple choice part of the test. So I hope you really understand what Newton's method is going to be doing after we do some examples in class. All right, ladies and gentlemen, that was section 3.8, Newton's method, aka finding roots. Your assignment is 1 through 18 even. Please work on these, y'all. I mean, it is what it is. And we're almost done with chapter 8, type 3. Good luck.